to interrupt me as we go along, or save your questions for the end. I'll try to take about 40 minutes today. Okay, right, we seem to be everyone's here who's going to be here, so why don't we crack on. And I want to first start by welcoming you and thanking you very much for joining in the webinar today. We did a similar webinar a week ago where I introduced some of the functionality relating to qNMR, and what I'll be doing today is to build on that by looking at concentration determination using NMR, and secondly looking at ways in which you can use this under automation. And these are ways that you can use that come straight out of the box. They're available if you have the plugin. Okay, so I don't know what's wrong with that. Okay, so in terms of an overview of what I'm going to cover today, we're looking at concentration determination. In terms of practical considerations, you can see some information on that on our website. I've written a few articles on that, but just to briefly say here that if you're looking at concentration as opposed to purity determination, you do need to make sure that your instrument's been set up correctly in terms of probe tuning and matching and data acquisition parameters. I'll come back to some of those in a second. You'll see how we can work around the ones that we can work around. But if you don't tune and match your probe, then the data that come out will be processed and assumed to be correct, but will in fact give wrong answers. So that's something you do. Okay, I can hear someone talking almost, yeah? No. Okay. Implementations, I'll show you how qNMR concentration determination can be implemented. There's a good number of ways this can be done. And integrity checking is the way in which we provide ways to determine that you or one of your users is using the software correctly, and therefore getting the correct answer, because it always does produce an answer, and you do need to make sure that that is the correct one. So the automation part of it is really just taking what we have in the top bit here and putting a wrapper around it that allows you to run this either in batch mode, which means that you might have a directory full of data which you want to push through and determine the qNMR data information, or you may want to do qNMR at the same time that you do verify, where verify is our name for ASV, structure verification. So what has to go along with this is several view.
I think the screen is closed.
Can you see my screen now?
Yeah, now it works.
Okay, thank you. Right, so we're talking about automation, batch operation, viewing the results of batch operation, and then finally we have the capability called a listener, which allows you to do real-time evaluation of qNMR information. So the workflow is going to be very, very similar to what we discussed last week, and that is to first process the data, of course, and due attention has to be given to things like window functions, and if required, you may need to do baseline correction. Depends a little bit on the data that comes off your particular machine, what you need to do here. And you can certainly specify processing templates to assist with this if you want to go for a more automated rollout. The multiplets are a number of nuclides. NN stands for number of nuclides. This can be done in essentially two ways. We discussed using auto-multiplets functionality with or without the structure. With having the structure is preferable. Or should you go for auto-assignments, that's a very nice way of proceeding. But you do need to have the prediction capability within the software to execute auto-assignments. And finally, you need the qNMR concentration determination. So the things that we need to talk about and discuss in some detail now are the following. We need to think about the way in which you do your integration, and I will expand on these in a second. There are 3 ways to do this. The way in which you convert area per nuclide, absolute area per nuclide, into concentration essentially falls into 2 main categories. One is using a concentration conversion factor, which is the name we give to it, or an internal reference, which might be solvent to uncertain peak. The selection of multiplets used to determine is a big subject, and we'll cover that in a little bit of detail today. And then finally there's reporting. So let's go through and quickly do an example just to show you how this would normally work for an average user without worrying too much about the setup. So I launch the program and I can open some data. So let me take one of these Spectrum. I'll get the structure as well while I'm here. This is obviously an easy case. So let's touch up the phase. It's not quite as crucial in this instance. You saw these data last week too if you joined in. Oop, didn't do a very good job there. Okay, and I'll quickly do some baseline correction. There we go, we're all done, ready to go. So let's do the multiplet selection, multiplets analysis. So it's going to go through, and what's done it, it's done the peak picking. So this is using the global spectrum deconvolution peak picking, followed by a classification procedure where it's found the DMSO peaks and the carbon satellites and bits of rubbish, the water peak, carbon, other bits and bobs, and then finally it's gone through and assigned each multiplet to classified each multiplet and determined the number of nuclides for it. So that's been done on the entire spectrum. That's all. I'm making this longer than it would be in real life. And if we go to qNMR concentration now, I can click on refresh, and it comes out with an answer, and I can paste a report onto the screen. In this case I've chosen a verbose report, which includes not only the results of this analysis but also all the data that were considered in deriving this result, so that if you need a bit of a trace back as to how this was derived and what data were used, then this can be put on the spectrum as well. So there you go. That's the whole deal really. That's all you need to do to determine a concentration if you have everything set up and ready to go. And this is the way it would be most of the time for you and your users. Okay, so that's easy example, and we now need to dig further a little bit. So if we consider the integration methods, this is quite a big topic really, whether you should choose global spectrum deconvolution, which is our deconvolution method. In cases of, I know I put you off this when I was speaking about purity determination, but in this instance with concentration determination and with the types of samples that you might be interested in for this, I would probably default to using GSD integrals. Some integration is certainly available, but you do have to watch out for congested spectra or spectra with impurities close by. In that case, some is not really a great choice. And if you are very interested in getting the very best data, then you can go on and do line fitting as well. So I've kind of put this for the purists. And I think 9 times out of 10, unless you're after the most accurate or precise data, then perhaps this is not necessary. So concentration determination can be done using our concentration conversion factor, and this is roughly equivalent to what's called PLCON by some users, and this is an empirically derived factor which you get from a spectrum of a standard sample. So you might make up caffeine or ibuprofen at 5 millimolar or whatever it happens to be, record a spectrum under particular conditions, and then bring the spectrum into Mnova, and then look at the conversion factor that gives you the right answer, basically, and that's the value that you're then going to apply to data in the future. The alternative way is to use the synthetic peak in the spectrum, which can be either electronically derived, as with Euretic, or added to the spectrum, as is the case with Qantas. And that's absolutely fine. Oopsie. And finally, some people like to use a peak that's actually in the spectrum, so it could be the residual solvent peak, the residual DMSO, for example, the DSS, or something that may be there that's put in a constant concentration. So that's really up to you how you do that, and all of these cases can be covered very easily within the software, within the settings. And once the setting has been done once, then it's applied every time, and you don't have to worry about it again. So you set it up once and you keep it in the library. Okay, concentration and libraries. Now, last time I spoke a little bit about the library that's used for purity, and we had something analogous with respect to concentration. So let's go back to the spectrum and dig a little bit deeper into the settings. So if I go to settings, the first tab is for concentration, and as you see, the first radio button selects internal reference, and this is set up at the moment for DMSO as a residual solvent peak. If I click on the reference peak as a solvent tick box, what the software will do is to look at the peak classification, and if it'll look to see which peaks are classified as solvent type, and it'll only use those. So if there are impurities or solute peaks in that range, then those will be ignored, and that gives you a good result, which you'll see in a minute when I show you some data. This is where you tell it that you want line fitting as well. But if I come to the concentration conversion factor, what you see is a whole bunch of data here. This is the actual number that's used. So this number multiplied by the absolute integral per nuclide gives the correct concentration, basically. And this is the empirically derived number that I was referring to a minute ago. So if you had 5 millimolar caffeine, then if you took the absolute integral of the caffeine peak, which is 1 proton, and you multiplied that number by this little number here, you would get 5 millimolar as the answer. Now, these data in these down below here are important, because it may be the case that when a different spectrum is recorded, the receiver gain changes, or the number of scans changes, or the pulse width changes. And if that is the case, that will affect the result that comes out. But we can compensate for it, luckily, and we do that automatically. So it's important that when you save away the data relating to the sample, relating to the spectrometer, really, it's important that you also record the receiver gain that was used, number of scans, the 90-degree pulse width. On a Bruker spectrometer, there's something called digmod, which also influences the absolute integral that's derived. There's the pulse program that was used, which is important, the name of the instrument, and the name of the probe. And it's important that all of these match up, otherwise the use of this number here will be incorrect. So what happens when new data are read in is that things are compared against these numbers here, or these values, for example, the instrument name, and if the instrument name is different, it was acquired on a different machine, then obviously this number is not applicable, and therefore the software will will alert you to that and refuse to do the calculation because it's not valid. So how do you keep track of all these things? And the answer is by using the library. So if I click on the library button, what you see is a couple of entries that I've made basically to cover different bits of data that I have. So what we're using today is acetaldehyde data that were kindly provided by John Hollerton at GSK. So that's the name I've given to this data set. And these are the values that go with it. And you can put a little note in here to say that for this number to apply, you need to prefer that you use some integration. And you can keep multiples of these. And the one that's used will be the one that's checked. So that all these things have to match, otherwise an error message is thrown. Okay, so that's how the libraries work, and I'm going to pause there and see if there are any questions on libraries, because that's a kind of a good place. Are we all okay with that? I take a silence to mean yes. Okay, cool. So let's put that to one side. Go back to PowerPoint. So this concentration on libraries concept is an important one, and I hope that's really clear with you now. Multiplet selection is something that we do to help improve the reliability of the calculation. So recall that rather than just choosing a single multiplet or peak within the spectrum and determining the concentration from that, what we do is to consider all the multiplets in the spectrum as targets for concentration determination, and we take an average of n of these. So if you say I want to consider 3 multiplets from the spectrum, what the software will do is to find some ways in which to find the best 3 multiplets that provide the best value of the concentration. And the way in which we actually determine the multiplets that fit those criteria are based on a couple of things depending on what you choose to do. So you can choose to do this by minimizing the RMSD. So clearly we're taking an average, and with the average comes an RMSD. And what we can do is to look at all the combination of 3 of the multiplets, the combination that returns the smallest RMSD. And in many cases that's sufficiently good to give you discrimination. You can, however, bias the software towards certain multiplets. I'm not going to spend a huge amount of time on this today, but I think I spent a bit more time last time, and there's certainly places I'll direct you to that you can read up about this in detail if you're interested. But we can do things like, for example, if you have a lot of perturbations in the aliphatic region of the spectrum, if you've done solvent saturation, for example, then you may want to bias the selection towards aromatic peaks. Aromatic multiplets is one example. Various ways in which you can influence the software to go off and find the best peaks, best multiplets to use for the concentration determination. So this is going to depend on your particular data, and if you're finding it difficult to work this out, then by all means send me an email, and I'll help you set that stuff up and get it right. But with all of these cases, once you get it set up once, then you don't have to touch it again. You just keep on using it the way you normally do. And you can certainly share these setups between your users. So once you set it up and you're happy, excuse me, you can provide that to your users and they'll do the same. They'll use the same data. The third option is to use a hybrid. So you can first order by multiplet selection and then choose the RMSD. So you can do kind of a meld of these two methods. Okay, so we've got a publication that's come out very, very recently that I can tell you about. It's available article in analytical chemistry, The link is here. It's an ASAP article at the moment, and one of the reasons that I can skimp a little bit on detail is to, first of all, spare those who aren't interested in that detail, and secondly, if you are interested in the detail, then please go to Analytical Chemistry and take a look at the article where all the detail is set out for you. So by way of illustration, I've got some data here where these are real chemistry examples, and what I've done is to run quantification 3 times. The first time was using GSD integration with certain multiplet selection rules. The second time was again with GSD using slightly different multiplet selection rules, and the third time is using sum integrals. And I hope you can see this on the screen, but the blue and the red or maroon columns track one another quite closely as you go across for the different samples, but you do start to see some differences with the green column, which is the sum integral. And the reason for this is that in this case I'm using the residual DMSO solvent peak as the reference standard. And in some of the samples, for example this tall one here, around 50 millimolar, this one clearly has got quite a differential here, and the reason for this is that there are some solute peaks close to the DMSO in that instance. And this is illustrating for you the one case where GSD integration is preferable, and how you can influence things in various ways. And so for this particular set of data, I would certainly advise using GSD integrals, and I would, in cases where I've got slight differences, for example over here between the two GSD methods, I'd look in those data to see which one is slightly better, and so on and so forth. So it's worthwhile going through a set of data and seeing what comes out of it, and using that to help guide you through what's the best way to proceed from there on. Okay, so I'm going to assume at this stage that all the basics of the concentration determination are clear in your mind, and that's all well and good. And what I want to focus on now is batch operation. And what you'll see with the batch operation is a lot of the stuff that we've been doing up until now will reappear and will be there exactly as you saw before. So what we have in effect is something of an engine within qNMR that you can use in various ways. So using it in batch operation or the listener mode are 2 ways in which to further enhance the way in which the qNMR can be applied. So let's look at those. I'll start the software. And so this was the manual mode. Recall from last time that you can change these selections, and if you wish, and play around with them. Right, so let's take a look at advanced qNMR automation batch. Right, so what we have to do here is to point it at a directory that happens to contain some spectra. So there we go, those are there. Select the folder. Within those there's a number and there's a FID, a file called FID within there. So there's a little tooltip to help you choose that. So you can use the standard wildcards like stars, asterisks and question marks there. You don't have to specify where the corresponding molecules sit, but if you want to, you can. It certainly helps, as I say, if they are available, and you can tell it where to put the results directory as well. So this is all the sort of overhead, if you like, to the necessary overhead that's required to do a batch operation. And when we come to these buttons, what you're going to see is something very similar to what you saw before. So here we go. This is the data this is the conversion factor for acetanilide. I can rev up the the library in the usual way. I can choose what integration method I want to use, whether or not I want to do assignments. So if I select this one, it'll do auto assignments on in each case as well. I'll leave it there for fun. The pre-processing has to do with whether you apply, how you apply your baseline correction and all that type of stuff. So in this instance, you may want to have, if your data require, you may want to have generated an MNP file, which is a processing template file, and point to it here. So that will be applied to the data as they pulled in. I don't need it today. The auto selection relates to way in which we select the multiplets. We want 3 multiplets. I'm going to keep it simple by just using the minimum RMSD selection rule. And the options here relate to a few bits and bobs, how you want to do your averaging, whether you want to calculate the area purity as you go along, and some reporting options. And when I click OK, it's going to fire off and do its thing. So there's 8 spectra to work on there. Okay, we're done. So there's a number of ways in which to interrogate the data. I have a second screen that you can't see, which has got, that points me to some other stuff. So I'm going to bring this on to here so you can see it. Right, so here's the results folder, and we've just made this folder here, and you'll see I've asked it to keep the Mnova files and a PDF of each of them. There's a text file with a summary of the results in it, or you can see it in a web form like that. Summary of each determination. Or if I go to this results file, oopsie, not from here. There's a results file here which I can access from the viewer. So let's go find that. Here we go, and the results.dat file. And from here, this gives you kind of an overview of each of them, each of the analyses. So, and at the same time, when you click on one of these, it loads the spectrum for you, and you can see how it did the calculation. Okay. There's various ways you can order these as well. Okay, so that's the simplest form of automatic operation. You have a directory that's loaded up with data, and you just want to grind through them and look at the results. So that's that. The last subject I want to cover is using the real-time listener. So what we're doing in this instance is we're basically specifying a directory. So it's going to be something like listen folder. In this case, this could be on the spectrometer drive, or it could be on a remote instrument, a remote computer server, depending on how you like to set this up. And the idea here is that as the data come off the spectrometer and are produced, you can automatically send those data to this folder, and the software can be running, and when it sees the data there, as soon as a file appears in this folder, it'll grind it through the analysis, and so the result is produced automatically. So this allows you to have within your open access environment, if you like, automatic generation of concentration information. Right? Okay, so I have to kind of simulate this because obviously I don't have a spectrometer here. So let's see. Let's make that screen a little bit smaller. Let's bring this to the fore. So what I'm going to do is I'm going to basically drag and drop data into this folder. Let's look first at the setup. So automation, concentration listener. So again, we have to give it some information. We have to tell it where the data are going to appear. Notice that you can specify more than one folder here. So you might have different folders set up for different spectrometers. The data are held in those folders. And then you need a mask for the type of file, and you need to tell it where the data, where to put the results. So I've specified the same directory here. Then if I go through the concentration, integration, pre-processing, all that stuff is exactly the same as what I've shown you 3 or 4 times now today. So I won't labor the point. This is all familiar to you now, I hope, and it does get carried over. So if you set it up in the UI environment and then come now to the automation environment, it will carry that information over, and it all has exactly the same meaning. The pre-processing applies. All of this is exactly the same, and when I click on OK, what it's going to do is not very much really. All it does is says, right, I've got the listener running, I'm listening to these particular folders, and it's just going to sit there and wait for data to appear. So here's my data folder, my listen folder, and I'm going to drag over some data for you. So I've got this on a different window. Oh, I don't want to move it. Okay, so there's, copy that over, and you can see it's doing the analysis. So I'll pull over a couple. Okay, there's another one, and one more. There we go. So we just sit and do that all day and all night if you want, but I don't want to do that today. So let's get rid of this. So I've got 11, 14, and 18 experiments that I've looked at today, and I'm done with this now, so I'm going to click on Finish and dismiss that and close that. And there you go. There's the results. So we did 11, 14, and 18. We can use the viewer in exactly the same way. Use it to recall the data, make sure that we like them, change them if we want. And the same other the web version of this report is generated as well as the text file too. So if you want to pick up that text file and do some further elaboration of it or send a result to someone or whatever, then that can be done as well. So this is there's several ways in which to pick up the results from these types of automated procedures. Right, I've really come to the end of what I want to say today, so I'm going to start winding up. So in conclusion, I hope that I've shown you that automated qNMR to determine purity and concentration, I should say, is very feasible. It's configurable to many, many analytical situations, conditions, and I hope that one of the examples I showed today may have rung a bell with you in terms of what you're doing. You do have to ensure that it's used correctly from the processing side, and that's handled for us in the libraries where we specify the spectrometer that was used and so on and so forth, and that's checked to make sure that that's right. And we have, in addition to the operations through the user interface, the ability to work in batch or on-the-fly operation, which is another way of saying listener operation. So with that, I'm all done today, and I want to thank you very much for your time. This is my email address here at the bottom, and feel free to contact me anytime, and I'll be happy to try and help you in this regard. We've still got a bit of time today, so if there are any questions, you can pop them into the chat window here. Everyone okay? Okay, I don't see any questions. I've either put you all to sleep or I've done a fantastic job of explaining it. So this is the final goodbye today, and again, thank you for your time, and I hope this has been useful to you and that you can see a place for this in your organization. Thanks everyone. Take care.
Mike, there's a question from Chen Pen.
Ah, okay. Chen? I can't hear it.
Chen, you can use the microphone if you want to ask a question.
No, I just want to thank you. So no question.
Thanks, Chen. That's very kind of you. Appreciate that. I know it's early in the morning for you in San Diego, so thanks for getting up, mate.
Thanks.
Okay, folks, have a good rest of your day or rest of your evening, and we'll speak again soon. Bye-bye now.
Bye-bye.